Section 2.5 Bounded Sequences. Definition. Let Sn be a sequence of real numbers Sn be a sequence of real numbers. Then we say that sequence Sn is bounded above if the range of sequence Sn is bounded above. Similarly, we say that sequence Sn is bounded below if the range set of sequence Sn is bounded below. Thus, sequence Sn is bounded if and only if there exists a real number m such that the absolute value of Sn is less equal m. That means the absolute value of Sn is bounded by a real number m, and it should be true for all positive integer n. So then, note number 1, if sequence Sn is diverges to infinity or minus infinity, then sequence Sn is not bounded. Why? Because there does not exist a real number m, so that Sn is dominated by that real number m. Number 2, a sequence that diverges to infinity must be bounded below. The next remark, an oscillating sequence, that means which is not a diverges to infinity or minus infinity, so the limit oscillates, so that the limit of the sequence is not unique. Oscillating sequence may or may not be bounded. For example, the sequence Sn equal to -1, 1, -1, 1, and so on continuously. Then Sn is bounded below by -1 and bounded above by +1, right? Even though it is divergent sequence. And sequence Sn equal to -1 raised to n into n for all positive integer n, then this sequence Sn is not bounded below and not bounded above also. Right. Then the theorem, the statement is, if the sequence of real numbers, Sn is convergent, then Sn is bounded. That means, simply speaking, the statement says that every convergent sequence is bounded, and the proof of the same is, let sequence Sn is convergent, and what we have to show? We have to show that it is bounded. That means there is some real number m which dominates the sequence, every term of the sequence, for all positive integers n. So Sn is convergent. So let us assume limit of sequence Sn is some real number L. It means, by the definition of limit of sequence, so for given any epsilon greater than 0, there must exist a positive integer n such that the difference of Sn and L is less than epsilon, and it should be true for all the natural numbers greater or equal the positive integer n. So what this implies? It implies that if I consider this thing modulus Sn, so it can be written as modulus Sn minus L plus L. So by using the triangle inequality, I can write it as Sn minus L plus absolute value of L for all n greater equal the large n. So by the definition, I have this quantity to be less than epsilon, right? So let m, I choose m to be maximum of modulus S1, modulus S2, modulus Sn minus 1. Then this thing, absolute value of Sn is strictly less than m plus modulus L plus epsilon, and it is true for all n belongs to I. Right. So it indicates that the sequence Sn is bounded by or dominated by some real number. That is, sequence Sn is bounded. What about converse? What you can say? So the theorem says that every convergent sequence is bounded. So what happens if we consider a bounded sequence? Does it converge or not? So the converse, but unfortunately the converse of the theorem is not true. That means, suppose if we take as an example, if we consider the sequence for positive integer n, so the terms of the sequence are minus 1, 1, minus 1, 1, and so on. So we know that this sequence does not diverges to infinity or minus infinity, and it is bounded sequence, is a bounded sequence. Why? Since if any term is less than or equal to 1, right? For all n belongs to I. But we know that it does not converges. Right? So let us see some examples. Give example of a sequence Sn which is not bounded but limit of Sn upon n is 0. So there are many examples. If I consider Sn equal to root n, then definitely the sequence does not converge, but Sn upon n is convergent, it diverges, but root n upon n converges to 0. Similarly, the second example, if we consider Sn to be logarithm of n, it diverges, but logarithm of n upon n, it also converges to 0. The next section is monotone sequences. Definition: let Sn be a sequence of real numbers if the terms are in this order: S1 is less equal S2, is less equal S3, is less equal Sn, is less equal Sn plus 1 continuously, then the sequence Sn is called a non-decreasing sequence. A non-decreasing sequence. Similarly, if the terms of the sequence are in this order: S1 greater equal S2, greater equal S3, greater equal Sn, is greater equal Sn plus 1 continuously by this way, then the sequence Sn is called a non-increasing sequence. A non-increasing sequence. And therefore a monotone sequence. A monotone sequence is a sequence which is either non-increasing or non-decreasing. Either non-increasing or non-decreasing or both. So this is the definition of monotone sequence. A monotone sequence is either non-increasing or non-decreasing or both. So for example, the sequence 1, 3 by 2, 7 by 4, 15 by 8 is, every term is increasing, is non-decreasing. Similarly, the sequence 1, 2, 3, 4, 5, which is sequence of natural numbers, is non-decreasing. And observe that between the first, between the two sequences, compare that, note that the first sequence is bounded. What about the second? But the second sequence is not. Also, the one more example, the sequence 1, 1 half, 1 by 3, 1 by 4 is non-increasing because they are in decreasing order and is bounded also, and it convergent also because it converges to 0 and it converges to 0. So this was the definition part. Now the theorem. A non-decreasing sequence which is bounded above is convergent. So to prove this theorem, let us suppose the assumption is that a sequence Sn is non-decreasing and is bounded above. So suppose sequence Sn is non-decreasing and bounded above. So let us consider the set A, which is having the terms of the sequence S1, S2 is non-empty subset of R, because Sn is sequence of real numbers, so every term is some real number, is non-empty subset of real numbers. And as the sequence Sn is bounded, so this set, which is subset of R, is bounded above also. Therefore, by using a least upper bound axiom, what is that? If a set is bounded above, then the supremum exists, right? So by least upper bound axiom, the set A has a least upper bound or supremum, right? So let us consider, suppose M is a least upper bound of the set A. Or least upper bound of set A. So now we wish to show that limit of sequence Sn is nothing but this least upper bound M. So the question is how to show this thing, that limit of sequence Sn is the least upper bound of the set A. So it means what we have to show? We have to show given epsilon greater than 0, the number m minus epsilon is not an upper bound, is not an upper bound of set A. Right? So hence there exists a positive integer n such that Sn is greater than m minus epsilon. As m minus epsilon is not upper bound, because m is least upper bound, so m minus epsilon is cannot be an upper bound of the set having the terms Sn, right? But since sequence Sn is non-decreasing, so it implies every term of sequence Sn is greater than m minus epsilon, and it is true for all n greater or equal n. So let me call this as equation 1. Now also m is an upper bound. M is an upper bound for set A. Therefore, m is greater equal every term of the sequence, right? And it is true for all the positive integers. So it implies that Sn is strictly less than m plus epsilon for all positive integers n. So let me call it as equation 2. So by using 1 and 2, what I can write? M minus epsilon is less than every term Sn, and every term Sn is less than m plus epsilon for all n greater or equal n. So by using the property of absolute value of real numbers, it means that, so it can be written as minus epsilon less than Sn minus m is less than epsilon, and it should be true for all natural numbers n greater or equal the large n. That means by using the absolute value of the real numbers, it can be written as modulus of Sn minus m is strictly less than epsilon for all n greater or equal n. So it means that limit of Sn as n tends to infinity is nothing but the real number n, and therefore sequence Sn is convergent. So we have considered that Sn is non-decreasing sequence which is bounded above, and definitely it converges to its least upper bound, right? The example: the sequence 1 plus 1 by n raised to n is convergent. So it is homework to you. The Sn is 1 plus 1 by n raised to n. So try to check that whether really it is a non-decreasing sequence. So try to check what it is homework to you, that show that S1 is less equal S2 is less equal S3 and so on. homework that it is bounded above. So it is a non-decreasing sequence. Then it is bounded. So by theorem, sequence Sn is convergent. Try to do the homework. And as limit of Sn as n tends to infinity is limit of 1 plus 1 by n raised to n as n tends to infinity is e. So this is the limit of the sequence and it converges to e.